Hello and welcome to Late Night Code. My name is Ian Riley, and I'm really excited to be bringing you another problem from the ICPC North American Regional Contest that took place this last February. The problem that we're working on today is called Champernowne Count. It is our first medium difficulty problem. It's currently rated about a 3.1, and I'm so excited to finally be in the medium difficulty for this channel. It's going to be a lot of fun. A couple of things, I just wanted to put it out there that there was a couple of videos where I said that the problem was from the Southeast Regional Contest for ICPC when that wasn't true. All of these problems are collected under the general header of the North American Regional Contest, but the North American Regional Contest is actually a collection of separate regions all hosting their own contest. There's Southeast, there's South Central, there's North Central, there's Mid Central, there's a lot of different regions. And actually in North America, each region is allowed to determine how they qualify people for the North American Championship, which means that they can all use different problems. So this collection of problems on Caddis is actually a collection of all of the unique problems that were offered by all of the different regions, or rather across all the different regions during the regionals contest period. So not all of the problems that we've worked on this channel have been specifically from the Southeast Regional, although most of them have. So I want to just be clear, these were all problems that were used in a North America Regional Contest of this year, but not necessarily from the Southeast Regional. Now, the Southeast Regional, one of the really nice things is that they're very quick about getting their test cases up, so we can actually make use of those test cases. The other regions don't necessarily provide test cases, but I'm currently contacting and reaching out for to coordinators in those regions to try to see if we can get access to their test inputs and their test cases. And I'm hopeful that we'll hear back, but I'm not sure. If I do, I'll try to make that data more accessible to all of you who might want to use it if you're going to be working on these problems as well. But again, I can make no promises, but I am working to try to get access to those test cases. If we don't have access, then we just have to use Caddis like we've been doing for problems like restaurant opening and Hunt the Wumpus, but that's just okay. The other thing I want to mention is that it is daylight because I am recording on the day that I'm going to be posting this up. So I wanted to record this last weekend, but this last weekend we had my son's baptism, which was an absolute blast. It was a great time. I had a lot of family in, but it also made it quite a bit crazy. And so I just did not have any time to record this past weekend. So I'm having to record today. It also means I'm having to postpone the other video that I wanted to work on. I really want to go back to our prior solutions and actually go through them with more in-depth detail on how we're solving those problems in Rust. So focusing on the language specifically, and also to kind of connect the dots between Rust and its application as a competitive programming language, which I think it could be a really good candidate for. And I'd like to see some new languages incorporated into our contests, Rust in particular. So that's something that I really want to do, but I think that video is going to be an hour to 90 minutes. I don't have that kind of time today, but I'll be able to get that to you later this week. So please just be patient with me if that's something that you'd be interested in. Otherwise, let's go ahead and jump into the problem in front of us. Champernowne Count. The nth Champernowne word is obtained by writing down the first n positive integers and concatenating them together. For example, the 10th Champernowne word is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all as one number. Given two positive integers n and k, count how many of the first n Champernowne words are divisible by k. Input. The single line of input contains two integers, n and k, where n can go up to 10 to the 5th and k can go up to 10 to the 9th. Output a single integer, which is a count of the first n Champernowne words divisible by k. That's all there is to it. Pretty short and sweet. So first things first, if you ever encounter a problem like that, one of the first things you start thinking about is a term called big integer, which is essentially a concept of how you can represent a number of arbitrarily with an arbitrary number of digits, basically of increasingly larger numbers of digits. Wow, that is a really bad way to say that. Basically just of an unknown number of digits. There we go. Big integer representing a number of an unknown number of digits. Now in this particular case, we actually have a number with not necessarily an unknown number of digits, but certainly so many digits that we can't store it in any given integer size. Not 32, not 64, not 128. We need an arbitrarily large integer size. And so that's what's called a big integer. So let's summarize this problem in that context. The first thing we're going to do is we're going to create successive Champernowne words. So you start with 1 and then move to 1, 2, and then move to 1, 2, 3. And the process by which we create them is just to concatenate the next set of digits. So the first Champernowne word, C1, if you will, would just have 1. The next one, C2, would have 1, 2. And so whatever that term is, that 1, 2, 3, all the way up to N, that number is what's concatenated to the previous Champernowne word to form the next one, and they are always numbers. What that means is that this number is going to have a large number of digits. Now, we don't exactly know how many digits we're going to be using, but we can come up with a fairly good approximation just by looking at the size of n. If you were to think about numbers, the first 9 numbers, so 1 through 9, all have 1 digit. So everything up to 10 to the 1 have 1 digit. Then from 10 to 100, so from 10 to the 1 to 10 to the 2, you have a number of 2-digit numbers. Then from 100 to 1000, from 10 to the 2 to 10 to the 3, you have 3-digit numbers. And hopefully you can kind of see the pattern here. If we were to say that n can go up to 10 to the 5th, then we would have a significant number of numbers that all have 5 digits in them. Okay? So if we're working up to 10 to the 5th, they're all going to have 5 digits. Just in the same way that when we work from 10 to the 2 to 10 to the 3, if we were to say that n is kept at 1000, 10 to the 3, they would all have 3 digits in them. So we can approximately say that we're working with 10 to the 5th 5-digit numbers. Okay? So effectively, numbers with about 500,000 digits in them. That is a lot of digits. To put that in perspective, a 64-bit integer can hold about 18 digits. And we're talking about, again, about 500,000. It's not exactly that, but again, it's just an approximation. That's not going to hold. And upping it to 128, not going to hold. So we need to be able to store an arbitrarily large number. And so we need an idea like big integer to represent that concept. Now, what we're going to do here is take these successive big integers and determine if they're divisible by a value k, where the value k here can go up to 10 to the 9th. So effectively asking the question, is some big integer divisible by some non-big integer k, right? And effectively we just need to count how many of those for which that would be true. It's a fairly straightforward problem, although the solution to this problem, although we can represent that concept of the big integer, we don't actually need one to be able to solve this problem. So let's jump over to Excalidraw to better understand what we're talking about here. So first things first, let's just quickly kind of discuss the whole notion of a big integer. How does that work? Well, if you were to think about a common number like 1, 2, 3, 4, 5, 6, then this is a number that could easily be stored in a 32-bit integer, a 64-bit integer, in 128-bit integer, and so on and so forth. And effectively the way that you do that is you just flip the subsequent bits that you need to flip in order to represent this in binary notation. For big integer, because of the fact that we know that the value of this number is going to exceed 32 or 64 bits, the numbers that they can represent, what happens instead is we stop thinking about these as being a corresponding set of bits and think about them with respect to their digits. And so one way in which you might think about this is to now represent it as a string of digits where you would encode each digit as a byte value. And so you could think about this, for example, as an array of bytes where this will be the byte for, and actually the way we typically represent this is have the least significant digit first. So this would be the byte for 6, this would be the byte for 5, this would be the byte for 4, and so on and so forth. And so what this does is it effectively allows us to store arbitrarily large numbers by storing them as arrays. But the consequence is twofold. Number one, the size of the number in this particular case is going to expand by quite a bit, right? If we're talking about a 64-bit integer, there is a large number of values that we can store within that number, right? Effectively, the first 10 to the 18th values we can store in that number. But what happens with this array notation is that for every digit, you have to use 8 bits. So an 18-digit number could be stored inside of 64 bits, but here we would need to use 18 times 8 bits, which is effectively 144 bits to store that same number. So effectively doubling the size in memory to store that number. Okay? The other thing that happens is that we don't have registers on our machine that can actually do all of the arithmetic to add up, divide, multiply, or subtract these numbers. And so as a consequence, we have to implement linear algorithms that can actually do the arithmetic for us. So if we wanted to ever add up like 1, 2, 3 plus 4, 5, 6, right? We can store both of these in we actually store them both in 16-bit numbers or 30-bit numbers, and we can store them in registers where the registers can actually just do the hardware arithmetic to add these numbers together. But if we were to think about these as now being big integers where these are actually arrays, well, then now we have to implement the kind of simplistic grade school algorithm where we iterate over them and we do, 3 plus 6 with a carryover. And so that's going to be equal to 9 with a carryover of 0. Then you're going to do 5 plus 2, which is going to be equal to 7 with no carryover. And then in this particular case, it's going to be 4 plus 1. Sorry to flip those around on you, but you get the idea. 5 with no carryover. And so we can take these two arrays and then we can produce the corresponding array 9, 7, and 5. Right? And so that's how we'd actually go about doing this in a big integer fashion. But note that's no longer O of 1. This is actually a linear time algorithm. Now, when things go to multiplication or division with big integers, we still typically do our grade school algorithms, but now the implementation of these things becomes more complex because while addition and subtraction work off of the least significant digit, multiplication and division actually work off of the most significant digit, which makes their processing, again, more difficult when we're talking about having to represent these with arrays. Now, what I'd like to focus on for this particular problem is the notion of division, because that's what we're actually being asked to do. And so again, I'm going to use this target number of 1, 2, 3, 4, 5, 6 just for fun. And we're going to go ahead and say here that's being divided by the number 1, 2, 3. And so to kind of bring you back to grade school arithmetic, effectively how we could do this is we would line up 1, 2, 3 inside this number. So we'd first line it up with 1, 2, 3. We would now determine the coefficient that we would multiply 123 by, which in this case would be 1. And then we calculate our remainder. So we subtract this off, we get a remainder of 0. And then now we got to drop digits down. So we drop down a 4, a 5, a 6. We put zeros up here. And then we go ahead and now multiply 123 again. We could do that 3 times. And that's going to give us 369. Subtract these off, and we're going to get a remainder. In this case, 31 plus 56. So that's going to be a remainder of 87. And then we would continue to do the division. And then that would produce for us that fraction. Okay. But if we were to talk about this in terms of its modular, or in terms of its modular arithmetic, we'd be talking about, in this particular case, 123 would be now multiplied by 1003 and then plus 87. And that gets us 123, 456. Okay. So this is effectively the algorithm that you would have to implement if you wanted to do big integer division, or at least it's one of the algorithms that you would implement. Effectively, you're kind of not getting away from something in this complexity class. Now, what's interesting about this particular problem is that we're not actually asked to produce this number on the top, right? Effectively, the problem doesn't even care what that quotient is. All it really cares is to figure out how many of the first in Champernowne words are actually divisible by k, where in this particular case, k would be equal to 123, and what's being divided would now be our Champernowne word. And what's kind of interesting about the construction of a Champernowne word is, by definition, some Champernowne word ci is actually equal to the Champernowne word ci minus 1 concatenated with I, where the concatenation here just means that you take the digits and you put them together. And why is that interesting? Well, one of the things that makes that interesting is because if you think about our quotient algorithm, what you actually have to do is take your k factor and then load it up or align it next to the most significant digits of your Champernowne word, and then iterate then across all of the digits of the Champernowne word. But effectively what happens because of the construction of our Champernowne words is that if we were to align to the first digits, we'd actually be aligning to the first Champernowne words, the C1 or the C2 or the C3 and so on and so forth. And then if we continue to effectively right shift along those digits, then all we're actually doing is just kind of moving along Champernowne words until finally we get to Cn. So actually in performing this division, this big integer style of division, we're actually iterating along all of the various Champernowne words. And so we can actually figure out at that exact moment whether or not they're divisible. And how would we know whether or not they're divisible? Well, every single time that we do this operation, we have to produce a remainder. And if that remainder is 0, like it is here, then we actually have it be that it is divisible. So in this particular case, the Champernowne word associated with 3, as we see right here, would in fact be divisible by 123. Whereas the Champernowne word for 1, 2, and 1, 2, 3, 4, and 1, 2, 3, 5, and 1, 2, 3, 4, 5, 6 are not, because those would all produce remainders. And so now the way we can kind of think about this is we don't even need a big integer because we don't actually care what the quotient is. All we actually need to do is implement the division algorithm and figure out how many times we produce a remainder of 0. And if we ever produce a remainder of 0, then it is the case that we have found a Champernowne word that's actually divisible by k. We also will need to keep track of the remainder, of course, because that's actually important. But yeah, so that's effectively the problem that we have on hand, is to just perform this algorithm. So let me go ahead and kind of talk real quick about the logistics of how that works. So the things that we basically need to keep track of is we would need to keep track of our first Champernowne word, which is pretty easy. Our first Champernowne word, which of course would be C1, is just the value 1. We need to keep track of how to produce next values of Champernowne words. So effectively, we're going to have some incrementer, where in this case, we'd have C1, which would be equal to 1, and then we want 1 to go to 2, 2 to go to 3, and so on and so forth. So we have effectively some I that we're incrementing on. We need to keep track of our current word. So we would need to have our current C, which would start out as 1, and then we would continue to add in these digits. Now, how do we do the concatenation without actually storing the word as a string? Well, the way you do the concatenation is you need to have a digit shift. So effectively, every single time we move up, then we just need to take C, we need to shift it over by some number of digits, and then just add I to it. Well, we need to keep track then of the number of digits in the current number. So what we can do is we can start off by just keeping track of the value 10, for example. So why the value 10? Because if you multiply a number by the value of 10, you shifted all of its digits rather over by 1. You always digit shift by the number of zeros when you're trying to do a decimal digit shift. So while I is 1, we would digit shift by multiplying by 10. That would shift everything over by 1, and then 2 and 3. Effectively, we keep doing that actually until we hit the number we're shifting by. So the moment that I becomes 10, then we just need to now shift by 100, not by 10. And the kind of cool thing there is effectively it's pretty easy. Just anytime I hits your shift, you just multiply your shift by 10, and then you do the shift. So that's pretty easy to keep track of. And then the last thing, of course, is that we've got k. We can now divide by k. We don't even need to divide, actually. What we can do is just kind of keep track of taking our c value, and then just take our c value and mod k. And of course, if that's ever equal to 0, if that's ever equal to 0, then we in fact have a Champernowne word that's divisible. Whatever, regardless of whatever it is, whatever that remainder is, that's actually what c becomes. So c just becomes c mod k. And so now we have this process where we take I, we keep incrementing by I. Every single time that we increment by I, we take C, which is effectively storing our current word, if you will. We multiply it by our shift, then we add I, then we mod K, and we see if it's 0. If it's 0, we up our count. Either way, we're taking that as our new value. Anytime I hits our shift, we multiply our shift by 10, and then we do the shift. That's pretty much all there is to it to actually implement this division. Now again, this won't give us the quotient at the end. All it allows us to do is to track the intermediate steps in the division process. But that's actually effectively good for us. If you wanted to know the quotient, by the way, you could still figure out the quotient. All you would have to do is just first determine what C integer division k is before you actually do the remainder. And that's pretty much all there would be to it. So with that, let's go ahead and jump into the problem at hand and actually go ahead and implement our Champernowne count. Going back to the problem at hand, what they tell us is that they're going to give us a tuple that's going to contain in and then k. So now we can go ahead and say let in k be equal to next tuple turboing into their types. U32 in this particular case, because in k, can go up to 10 to the 9th. And this is the only input we're taking, so we'll just go ahead and pass a mutable reference to a new string. And that's pretty much all there is to it. I did typos, let's fix that. Now we've got our tuple. So then the next thing that we have is we're going to have an I variable that will iterate over k. So we can say for I in 1 up to and equaling n. There we go. And so I will now start with our first term and then continue to increment up. I also mentioned that we would need our Champernowne. So we're going to say let mut c be equal to 0 in this case. And I'm just going to have that go ahead and be a U32 because it'll always be a positive number. Okay. Also k is a U32, so might as well keep them to being the same. Now, I should go ahead and kind of stop to think real quick, though. because I've made N and K U32, which makes sense for the strictness of their type. But I'm also now saying that our Champernowne word won't get bigger than a 9-digit number, which I don't think is technically true. Because if we think about our Champernowne words, if you have a number that's not divisible by K, then the entire word will now be mod K, which means that it is limited to a size of 10 to the 9th, but then it'll have to get shifted. And technically it could get shifted by up to 10 to the 5th. So we could be dealing with effectively 14 there. So a 10 to the 14th size number, which cannot be stored in a U32, but can be stored in a U64. So I'm going to go ahead and be a little bit pessimistic here and just say U64. I think that that is appropriate. Because again, if we're going to mod it by a number that's 10 to the 9th, it'll always come back down to a number that's 10 to the 9th, but then it has to be shifted by a certain number of digits. And we said here that we could potentially shift it by a 10 to the 5th. And so we just need to be careful here. And so I'm going to say that this is going to be a 64. Because if you digit shift a 10 to the 9th number, you already bust a U32, because that's actually the largest number it can store. I can't store a 10 to the 10 number. So we're going to go ahead and say U64 here. And then the only other thing I would need to keep track of is my shift. My shift is capped at 10 to the 5th. And so now we'll go ahead and say let mute shift, and that's going to be equal to a 0 U32. Okay. So now I have my different variables. We have N, we have got K, we got C, we've got shift, we've got I. And so now we can go ahead and go through the process of actually calculating our next C and then determining whether or not we have, a count. Let mute count be equal to 0. There we go. So first things first, we need to determine if we should increase the size of our shift. Our shift needs to start at 10. There we go. And then to increase its size, we increase it anytime that I becomes equal to the shift. So if I is equal to shift, then shift is now times equal 10. Okay. So that's how we do that. Then the next thing is that we need to go ahead and shift C here. And so we can say that C is going to be equal to or times equal to our shift. Then the next thing is that we would need to go ahead then and mod C. And so then we would do something like C is equal to C mod K to determine what the remainder is. And because I'm doing both of these together, let's go ahead and just simplify the process. C is equal to C times shift as U64, okay, modulo K as U64. And now that will take care of both of those operations at the same time. Then afterwards, we just need to know if C is equal to 0. So then we just say if C double equals 0, then count plus equal 1. And that's basically all there is to it. And then at the very end, we've calculated our count. So we can come over here and now, so go ahead and delete up to that. Go ahead and insert these, and then just go ahead and output our count. Okay. Let's go ahead and talk about what's going on here. So we're going to be looking at our Champernowne words from 1 to N. Do we know, in fact, that we are producing these? Well, if we go and look at this, what ends up happening is we are missing one little term here. So we shift the C, then we add I as U64. Perfect. Okay. So effectively, we're going to take the I number and we're going to add its digits into C by adding them at the least significant space. In order to make room for all those digits, we are going to shift C. So effectively, C will start at 0, shift by nothing, and then we add 1. And then we'll go from 1 to 12 by effectively taking 1, multiplying by 10, and then adding a 2. So now we have a number of 12. And we can keep doing that. We can keep making space, so making zeros for our least significant digits to store I, and then storing I in those least significant digits. Now, in order to perform the division as we know it, we then mod by K, determine what our remainder is. If we ever produce a remainder of 0, then we increment our count because we found a Champernowne word that is actually divisible by K. We always need to make sure that we're keeping track of the number of digits that we need to open up for I, and so we maintain this shift. If I is ever equal to shift, that means that we now have produced another number with a new digit, and so we now need to increase our shift, and we just shift it by 10. And that pretty much handles all of the logic that we need to be aware of. And at the end, we just go ahead and print our count. So then here, let's go and open up a new window and let's go ahead and get our sample text 4 and 2. We'll go ahead and clip that into our cargo run -- s Champernowne count. and we get the value of 2, which is what we wanted. We'll take the next sample. We get 14. We'll take the next sample. We get 4, and we'll take the next sample, and we get 1. So all of this is looking really, really good. So the next thing for us to go ahead and do is to go on to CADIS and go ahead and submit this and see if we can pass all of those test cases. Okay, and with that, our solution has been accepted. We have passed 101 test cases. They put a lot of test cases in there. We've passed them all, and we've successfully solved Champernowne Count in Rust. I hope that you enjoyed this video and are looking forward to the next ones. We'll be moving on to repetitive song next, and I'll also be getting that video out to you on Rust later this week. Till then, have a great night.